Okay, folks, I want to offer a little tutorial on the first evaluation content. I want to do two things with this. One is to kind of re-engage the concepts around which these ideas are built. And then as we kind of go forward from that, then I have a data file that I'm going to pull up in JASP, not like your evaluation data file, but a data file that I'll pull up in JASP, and I'll kind of walk through the process of performing the procedures to generate the data that you're going to need. Now, I'll probably only deal with one case, one scenario of each type of procedure, and so be aware that the evaluation requires you to do perhaps more with that, or look at more than one particular dependent variable. So anyhow, there are two basic concepts laid out in this evaluation. One is looking at descriptive information, general descriptive information, and making or looking and answering some questions related to the way in which data is distributed. Now, we're looking at primarily continuous data here as a dependent variable. And so it will be, we'll be looking at concepts like mean and median and minimums and maximums and different sorts of things to look at, which will play out in your first evaluation. Now, what you have to be aware of is that once we put these on one evaluation, then they'll keep folding them into subsequent evaluations. So it's not like you deal with these things one time and then you kind of move off of them and move on to something else. And so with all that being said, let's see if we can kind of get into this a little bit. One of the main concepts that we talked about, and let me see if I can get a share up. Let me get a marker here that I can work with. Okay. As we may have talked about and did talk about earlier quite a bit, at the center of all the logic pertaining to basic statistical analysis, and particularly that analysis dealing with continuous variables, is this notion of normality. And the most basic normal distribution, or the most predictable normal distribution, I guess, is a distribution of standard scores or distribution of z-scores. And so we're going to use that as kind of the jumping off point, not because we're going to talk about z-scores in this evaluation, but because the logic kind of begins there. And so in general, the way normal distributions work is that the center of the distribution is the mean, and that'll be represented if it's a population by the Greek letter mu, and if it's a sample by x bar, which is talking about sample means. And in this case, since we're talking about distribution of z-scores, or a sort of a grand mean sort of idea, 0 is at the mean for raw value. Then you go up one standard deviation unit, and this little sigma here is representative of standard deviation. You go up 2 standard deviation units, you can go up about 3, you can go down 1, down 2, down 3. Theoretically, this curve never reaches the axis, but for all intents and purposes, it's really hard to find distributions that have z-value is greater than 3 or less than -3. Yeah. These are symmetrical distributions, and so you know, around the mean, what it looks like on one side, it looks like identically on the other side. Standard area curves means that about 34% of the cases, or the area under the curve, lies between 0 and 1 standard deviation unit up, and 0 and 1 standard deviation unit down. And about 13.5% of the cases, these are not exact numbers, about 13.5% of the cases lie between 1 standard deviation unit and 2 standard deviation units. Excuse me. And so between 1 and 2 are about 13.5% of the area under the curve, or 13.5% of the cases in a normal distribution. And then the rest of it lies beyond 2 standard deviations. Well, when you think about that and look at it a little further, that means that about 68% of the cases, over 2/3, lie between 1 standard deviation unit below, 1 standard deviation unit above the mean. And about 95% of the cases lie between 2 standard deviation units above and 2 standard deviation units below. And so if you wanted to find what were the limits, in other words, the minimum and maximums of the middle 95%, you would start with a mean value, subtract 2 standard deviation units from it to find the minimum, add 2 standard deviation units to it to find the maximum. Now, another concept that's related to this is the notion of what are called central tendencies. And central tendencies, there are actually 3 of them, but there are only 2 that really are terribly useful to us. And one is called the mean, and the other one's called the median. The median represents the point at which 50% of the cases are above the median and 50% are below. The mean is simply the arithmetic average. Now, if you think about a standard distribution, that means that the mean and the median are at the same point. So whatever the mean is would also be the median, because that would represent the point at which 50% of the cases are below and 50% then would be above. Now, most distributions are not this neat and nice. And so if, as it often happens, the mean and the median are different from each other, it's important to know what that means. And so if the mean value is greater than the median value, let's say this represents the median here. If the mean value is actually greater than the median value, that means the distribution is skewed what is called positively or to the right. In other words, there are outlying cases in a positive direction that will drag the mean higher than the median. Conversely, if the mean is lower than the median, that means the distribution is skewed negatively or skewed to the left, because there are outlying cases out here somewhere that are dragging the mean below the median. And so the thing to keep in mind is whichever direction of the median the mean lies, if it's above it, then it's skewed to the right, it's positive skew. If it's below it, then it's skewed to the left, and it's a negative skew. And sometimes it's important to understand you know, that skewness of the distribution, so that you can make decisions about whether an outcome is a meaningful outcome or not. because if a distribution is not anywhere near normal, then it becomes a little difficult to, make generalizations about what a particular mean or whatever would relate to a larger set of numbers. And so in a lot of cases, and particularly when you're dealing with individual cases, it's important to know which way the distribution is skewed. Okay. The second main concept in this evaluation is the concept of the t-test. Let me see if I can, or the t-distribution, see if I can get that little graphic to come up. Okay. And, t-distributions, there really are, two varieties of it. Now, one of them, either one of these two varieties can be used for the third case, which we'll talk about in a minute. But let's say that we have a population distribution and in which the grand mean is here. In other words, the overall population mean is here. The mu is here. And we have two groups that are drawn from those populations, theoretically, hopefully random selection. And so we have group A and group B. And if we have the mean of group A, the X bar represents the mean of a sample. So the mean of group A, and then we have another distribution for the mean of group B. And if those are two independent separate groups, we would want to know whether that distance between these means, A and B, lies within the range of what we would think would be a random fluctuation between means. And that's that middle 95% range of sample means. Conversely, if we find that this distance between A and B, mean of A and mean of B, is greater than is in the middle 95% of a distribution of sample means, then we have a significant difference between those two groups. And that's called an independent samples t-test, because we have two separate samples. Now, the situation is very similar in terms of post and pre. If we think of post-test and pre-test being kind of lumped together in one set of scores, we can think of it in a very similar way, because there will be a distribution and a mean for pre-test scores. There'll be a distribution and a mean of post-test scores. And then there'll be a grand mean around all the possible differences between individual scores of individual subjects. Individual scores of individual subjects. And the question we ask then is the difference between these pre-test mean of individual subject scores on the pretest significantly different from the mean of the potential post-test scores of individuals on the post-test. And if this lies within the 95% range of all possible differences between individual subjects' scores pre and post, difference pre and post, then we say that's just a random difference. If it lies outside of that middle 95%, then we say it's a significant difference. Now, if we think about, and that's a paired t-test, P-A-I-R-E-D, paired t-test. If we just think about this distribution up here, instead of worrying about, let's say group B, we want to know whether group A mean is significantly different from the grand mean, and that's called a one sample test because we're comparing one sample to a grand mean. And what we're trying to establish is whether the distance from this sample to the grand mean lies within the 95% distribution of all possible differences between all possible samples and the grand mean, or is it outside of that middle 95% and therefore not random, and we would call it significant. And so there are three t-tests that we run. There's the independent t-test between two samples from one population, the paired samples t-test, which is most often described as a pre-post, doesn't necessarily have to be a pre-post, and a one sample t-test, which is the difference between a particular sample mean and the grand mean. And so those are the two basic concepts that are on this evaluation. Okay, so let me tell you about this distribution, about this sample that I'll be playing with a little bit here to show these ideas. And it's a sample based on a piece of research I did a few years ago where we were looking at adjunct students at community college level and how well they fared based upon the level of adjunct instruction they had as compared to, you know, the students that had maybe a higher level of full-time faculty instruction. And we looked at one semester, we looked at their first full-time semester. And so there's data in here about things like gender, GPAs, you know, different sorts of things. And so we're going to use that as an example of how to get at these concepts of descriptive statistics to talk about the nature of distributions and how to work with the different t-test varieties. And so for your evaluation, it's simply looking at a different data set and looking at different variables. But the actual processes will be identically the same. Now, I will save this particular example out as a JASP file and post it up along with the link to this particular video. So let me jump over on that JASP file. I don't know why that did that. Okay. Okay. So I can get this to share up right. All right. I'm going to open a file and off of my computer, and the file is called adjunct sample. And so I went to the folder that I'd saved it in and simply browsed and clicked it up. As you can see, it's a, you know, it's a fairly significant data set, and it has lots of different variables to play with. And I'm going to reset all this. Because I was doing something else with it. And so we're going to run a different procedure. We're going to run descriptive statistics. We'll look at GPAs the first semester. And cumulative GPA at the end of year one. Okay. We're going to, in terms of statistics, accept some of the defaults, but we're going to add a couple. We're going to add the median value. We're going to take out the minimums and maximums. Those are easy, and it's a little confusing. Minimums and maximums are generally it's just the lowest value and the highest value in the data set. And so I think that's all we need there. Yeah. And so then we'll go over and look at the output. And so I have GPA semester one, cumulative GPA year one. I have the mean, the median, and the standard deviation. Now, if you will look at these, first off, you can see the mean is lower than the median in both cases, which means that the distribution of GPA semester one, GPA, cumulative GPA year one, the distribution of those are skewed to the left in a negative direction because the mean is below the median. And the standard deviation is 1.22 and 0.88. So if I were to ask what would represent the middle 95% of scores, the middle 95% of scores for the first semester GPA. Thinking about the normal distribution and thinking about what represents the middle 95%. That means it would be the mean minus 2 standard deviations on the low side, and the mean minus 2 standard deviations, plus 2 standard deviations on the high side. And so the mean here is 2.63, and the standard deviation is, say, 1.22. Mean is 2.65, rather. And so if I double the standard deviation, and so instead of 1.22, it's 2.44, then it's on the low side, the bottom, the 5 percentile level, or the 2.5 percentile level, rather, is 2.65 minus 2.44. And the top is 2.65 plus 2.44. And so it's roughly about 0.19 on the bottom, and at the top it's, what is that? 5, roughly 5 or so. Now, obviously the 5 is absurd because GPA only goes to 4, but it tells you that, that this distribution is pretty well spread out, and the middle 95% would be represented by 2 standard deviations below the mean, up to 2 standard deviations above the mean. In the social sciences, sometimes that's referred to as the rule of 2s. And but that's the way you would establish, the middle 95%. Yeah. Let's ask the question related to say pull down the t-test menu here, if I can get it to come down. There we go. We'll ask the independent samples t-test first, and we'll use a dependent variable GPA first semester, and we'll use gender as a grouping variable, in other words, sex. I hope there's not some outliers in there. We'll have to kind of see. And we'll run what's called an independent samples t-test. That's what we pull down. We want to know is group 1, or our assumption is that group 1 is not equal to group 2. That's what we call our alternative hypothesis. We'll include, well, actually, we don't need to add anything to this one in that effect. And so if we go over to the next panel, we'll see that the GPA for semester 1, the t-test value, degrees of freedom, and the significance level. And as always, the significance level is our starting point. If it's less than 0.05, that means that there is a significant difference between genders. And as a matter of fact, let's add descriptives into this so we can identify the genders. So the females had a significantly higher GPA first semester than males, 2.76 versus 2.519. The significance level of the p-value is less than 0.001, which is less than 0.05. And so in the display here, you see the actual t-value itself, the degrees of freedom, which is the n-1 for the total group, the number of females 794, the number of males 630, standard deviations 1.20, 1.21, and then what's called standard error, which is essentially the if we look at mean values, potential mean values for different groups, this would be the equivalent of a standard deviation for those mean values, group mean values. And so the answer would be yes, there is a significant difference. And if I explain it, the difference is that females had a significantly higher first semester GPA than males. Now, let's ask the question as to whether there is a significant difference between the first semester GPA and the first year GPA. And so that's a paired sample. We treat it as if it's a pre-test, post-test, because it's a measure of the same thing expressed in the same scale. And so it's a paired samples t-test because we're talking pre-post. The GPA semester 1 is part of that sample, and cumulative GPA year 1 is the other part of it. We'll do descriptives and look at what we find. Paired samples t-test. P-value is 0.168, which is not less than 0.05, not less than 0.05. So therefore, there is no significant difference between GPA for semester 1 and the cumulative GPA at the end of the year. And you can actually look at the means to get an idea. First semester was 2.65, the end of the year was 2.81. But because of the difference in standard deviations and the different standard means, that meant that there was nothing really happening there. There was not a significant t-value. So we always start with the p-value, which is the, we always start with the p-value, which is actually the chance of being wrong, if we had said there was a significant difference from GPA semester 1 to GPA year 1. In other words, that's the possibility of a false positive. And we always want the possibility of false positive to be less than 0.05. In this case, it's almost 17%. And so that's a bigger risk than we're willing to take. Okay, let's ask a third question. We'll go to the one sample test. Let's ask the third question. Let's say that we know that the average GPA per year across the entire community college system in this state, the cumulative GPA at the end of year one is normally 2.72. 2.72. And so we have a test value of 2.72. And we want to know if this particular group cumulative GPA at the end of year one is significantly different from the system-wide average for GPA at the end of year one, which we have set at 2.72, because we know that from some other data source or for some previous calculation. And so we want to know if cumulative GPA year one is different from this test value. We'll run descriptives. And we find that indeed it is. The p-value is less than 0.001. And because the mean locally for this one community college is higher than the test value, in other words, the sample mean for this community college is higher than the grand mean for the entire system, then we can say that this particular community college had a significantly higher cumulative year one GPA than did the community college system in this particular state. And I believe those are the only concepts that you need in order to do the first evaluation. Now, as I mentioned, I will put up this video on YouTube, put a link to it on As You Learn, and I'll also put up the JASP file that I just did so that you can have that to kind of walk through if you want to walk through that and look at this, sort of different data set. So I'll save that out. I'll put that up on As You Learn, and I'll plop this video up on YouTube. Yeah. Hopefully later today, I will also create another video to introduce you to the next topic areas, which are analysis of variance, correlation, and regression. And if I don't get that done this afternoon, it'll be Saturday, probably before I get that one done. I'll be on the road tomorrow, but next 2 days. Okay. Well, folks, hopefully this helps, and good luck on the first evaluation. Have a good evening.